just revise what we did last time quickly, so we are sure that all of us are in the same page. Is it fine? Can you hear
Yes.
me? Okay, this is very good. So we can go quickly through the slides here. I mean, last time we talked about what is the difference between artificial intelligence, machine learning, and deep learning. And we agreed that artificial intelligence, this is a big umbrella, and underneath it we have machine learning. Machine learning, in fact, it's black box models. On the other side, we have something else which called white box models. And those white box models, maybe it could be statistics, it could be expert system. It's a system where we can understand the relationship between inputs and outputs, and also we can understand the mapping between inputs and outputs and how decisions are taken. So, for example, if you are building an expert system, rule-based system or case-based reasoning, it has it has the ability, in fact, to understand which rules has been fired and to understand why the system has been taking this decision, for example. Underneath machine learning, we have deep learning, because we have also, we can just say that we have shallow learning, and the shallow learning and the deep learning. In shallow learning, for example, we have lots of algorithms. We have supervised and unsupervised learning. We have reinforcement learning and so on. So machine learning model transform its input data into meaningful outputs, a process that is learned from exposure to known examples of inputs and outputs. So I mean, in deep learning, it's supervised. So we need to have examples of inputs and outputs, and we try to learn this pattern of how can we map inputs into outputs. In deep learning, we can work also in shallow learning, in fact, and it could be somehow deep if we can use different types of layers or number of layers, and each layer will try to learn some representation from data. And the deep, it's not referring to any kind of deep understanding, but it refers to just the idea of successive layers or deep layers, deep representations of our data. So for example, here in this example, maybe this one, it's MNIST data set. For example, we have digit, or this is original digit, and we need to classify it into number 4, for example. So each layer will try to learn some representation, and it will send it or will transfer it to the next layer and so on, until we can make some decisions, until we are able to make some decisions. Learning process, it's the same. We have inputs. We apply those inputs to some layers. Those layers have some weights. This layer will transfer those inputs using those weights. We initialize those weights with random values, and we will make some calculations, activations, and it will transfer those numbers into the next layer until we can have some prediction. And we have those predictions. We will subtract predictions from target values. For example, we will calculate a loss function, and we will try to use an optimizer to adjust those weights and bias, for example, in a way to minimize the loss value or loss score, for example. If you are working with Keras, we have very nice way for plotting those intermediate values, because sometimes people are just curious. They want to know what is the output from each layer. So in Keras, in fact, it's very easy to do it. So you just need to define temporary model using model API. So this, each time we will deal with the model from the beginning to this layer which we are interested in. So for example, if you have a model and this model has, for example, maybe it has, for example, 3 layers, for example, or 4 layers. It will be something like this one. So if you want to plot the output from the second layer, for example, in this case, I need to define a submodel from the input to that layer. So this is the case here. So we are not slicing it into layers, in fact, but if you are interested in plotting the outputs from one specific layer, you define a model from the input to that layer, and you will provide the input. After training your model, you will provide the input to the input layer, and you will get the outputs from that specific layer, and you can just plot it, for example. So for example, here in this example, we have MNIST data set, and we need to plot the outputs from one of the hidden layers. I don't know this model, this model, maybe it has only one hidden layer, so I want to plot the output from this hidden layer. So I will define a model. The input to the model will be the input to our original model, and we will take the output from this specific layer which we are interested in. So this is a submodel or temporary model, and you will just get those outputs because predict. So now I define the temporary model. I will use this temporary model for predict for some test values. So you will apply the test image here. I applied here 10 images, for example, 10 images, and I will try to predict what is the output from this hidden layer. So this is the case here. So in fact, you can use the same test example for predicting which class you will get, for example, each time from the original model, because this outputs we can get it from our original model. But at the same time, also you can define a temporary model, and from this temporary model, you can get access to those intermediate values or outputs from some hidden layers, for example. So this one, for example, we will get it from this model, but this one, we will get it from the original model. So sometimes people are, curious. They want to see what are those intermediate values, and it's nice. So for example, here we have some input digits, for example, and each one it's correctly classified into, for example, this one it's classified into 7, this one classified into 2, this one classified into 1, this one classified into 0. But sometimes we need to see those intermediate values which are generated from each, the representations which are produced from each hidden layer. So in this case, we can try to get those values. Convolutional layer. If we will go into shallow learning, in shallow learning, we don't learn any, we don't try to extract any, automatically extract any features from the data set. So we cannot work, in fact, in reality, we should not work with raw data, but in convolutional neural network, we work with raw data. So the goal of CNN here is to learn a higher order feature in the data using convolutions. And the convolutional layer is responsible for systematic applications of one or more filters to an input. Those filters, we use those filters in general. If you are working with an image, for example, we use those filters to extract some features or feature map from the original image. And usually, if you are in shallow learning, we should do this process manually, in fact. If you want to help your model, so instead of applying those digits, those original images, pixel by pixel, so the model will be very large. Maybe the model, we need more data, in fact, to train our model. We can try to extract, we can apply those filters, for example, to those images, and try to detect edges, for example. So for example, I have here 7. If I will apply some filters, maybe I can extract something like this one, right? So maybe this is very enough. Or try to extract some features from the image and apply it to your model. So in fact, in CNN, we do this one automatically by just defining a number of filters, and those filters will try to extract some features which can help the model for learning my data. So in CNN models, in fact, it's deep, in fact, because sometimes we can just use maybe 20, 50 layers, hidden layers, for example, or layers, convolutional layers, followed by fully connected layers. But those filters, you decide it by yourself. How many filters we need to apply, for example. Usually in the input, we apply less number, and when we go deeply, we apply much larger number of filters. So the architecture consists of 3 types of layers. We have input layer, and this input layer, it will just transfer the images. If we are working with images, for example, it will transfer it into the next layer. And after that, we have some feature extraction layers and the classification layers. Those are the most important, right? Feature extraction layer and the classification layers. In shallow learning, in fact, we don't have those feature extraction layers. We have only classification layers, or you can call it fully connected layers. So in the last example here, if we are working with MNIST dataset, we can just build a simple model. And this model, for example, it can consist of, for example, 2 hidden layers and 1 output layer, for example. So we don't have any feature extraction layer. We can consider all those layers as fully connected layers. You can just call it FEC1, FEC2, FEC3, for example. And we have here inputs. We apply the inputs to the, we can call this one the input layer, right? So this one, it's input layer. We have some classification layers, and we have some or hidden layers, and we have some output layers. So this is shallow learning. But in deep learning, in fact, we have feature extraction layers, which is repeated sequence of convolution and pooling layers, and we have classification layers, which we can call it fully connected layers. So here, for example, we have this convolutional layer number one. For example, we need to extract. I mean, we need to apply some filters to the input image to extract a set of feature maps. And after that, we can apply pooling layer. And when we apply pooling layer, we try to generalize. We try to reduce the size of the feature maps, for example, using pooling layers. Because if we are using a pooling layer of 2 times 2, we can get rid of 75% of the activations. In fact, I mean, last time we talked about activation, because when we apply those filters, we apply each filter and we move it, for example, by 1 step or 2 steps, 1 pixel or 2 pixels. Each time when we apply it to some receptive field, in fact, we have an activation. We do some calculations. We have one activation and we move it 1 step and do another activation and so on. So in fact, one way for reducing those number of activations or calculations, we can use those pooling layers. So those pooling layers will try to simplify or to reduce number of calculations, maybe by 75% if you will do 2 times 2, for example, with stride equal 2. So if the pooling size is 2 times 2 and stride equal 2, so in this case, I will apply it and I will move 2 steps or 2 pixels, apply it 1 more time and so on. In this case, in fact, we will reduce the feature map from its current size into 25% of its size. So we will get rid of 75% of the whole area, in fact, or the whole, height and width of the feature map. And when we reduce it by 75%, we will reduce number of calculations or number of activations. So in general, we have those feature extractions, classification layers. So we will do those feature mapping, pooling, feature mapping, pooling, and so on. We can repeat this process several times. And at the end here, we will have something called the flatten. We will flatten those feature maps. I mean, at the end here, we will get some feature maps. We will flatten those feature maps. Flatten means we will try to put it as a 1D vector, and we will apply those values into a fully connected layer. Maybe you can have 2 fully connected layers, 3 fully connected layers, it's up to you. And of course, when we apply those successive pooling, in fact, we will reduce the feature maps at the end. And in this case, you can just say that we will reduce the size of this fully connected layer. And when we reduce the size of this fully connected layer, we will reduce the number of parameters in my model. And then when we are reducing the model number of parameters, we are reducing model capacity, and we are reducing the chances of overfitting. So in fact, pooling is very important for 2 reasons. It's for reducing the number of activations and reducing the number of calculations, so we can make a learning process much faster. And at the same time, also we can overcome this overfitting problem. Yes. So in general, it's feature extraction layers, a number of feature extraction layers, and number of classification layers. So in this, I mean, again, sometimes in some places they call it 3 types of layers in CNN: convolutional layers or feature extraction layers, those pooling layers, and fully connected layers. Each convolutional layer, it consists of filters and feature maps. Those filters, in fact, we decide it by ourselves. You decide it. What will be the size of the filter? So some people can say that, okay, I will use 3 times 3. Some other people can say that, no, I will use 5 times 5 or 7 times 7, for example, correct? And when we apply those convolutional filters to the original or to the root data, we will get some feature maps. So the size of the feature maps also, it will be based on the selection or the combinations of number which we will use. So the filter size, stride, pooling, padding, based on this, you can decide what will be the size of your feature map. The filters are essentially a neuron of the layer, in fact. So for example, when we say that I will use a filter which is 3 times 3, for example, times 32, you can just imagine that each filter from those will be 1 neuron. In fact, it will be 1 neuron in the in this feature extraction layer or convolutional layer, and how many of those neurons, it will be 32, for example. Right? And this is how we calculate a number of weights. So you can just imagine that I have an input image, I will apply it to the convolutional layers, and I'm using 32 feature maps. So when you select 32 feature maps, we will create, in fact, 32 neurons, and each one, in fact, it's connected with this number of weights, 3 times 3. If your image is one channel, so it will be 3 times 3. If your image is 3 channel, so it will be 3 times 3 times 3. It will be 27. So imagine it's a 3 times 3. So each neuron, it will be connected with 9 weights. So it will be like omega 1, omega 2, until we have omega 9. And each one will be like this one. And of course, we have bias here. So when we calculate number of parameters, of any convolutional layer, in fact, we multiply this number by this number by this number plus 32 number of filters again, because this is a bias. So this is how we calculate number of parameters, right? So if you have the feature extraction layer, for example, and you have this filter size, you have this number of features which you want to extract, feature maps. So how can we calculate the number of parameters? So it will be 3 times 3 times 32 plus 32. If your input image is 3 channel, which is RGB, for example, if your image is RGB, so people also select the size of the filter 3 times 3. They don't select 3 times 3 times 3, right? We just select it 3 times 3 or 5 times 5. Number of channel, it will come automatically from the input data. So don't need to specify it. But you need to consider it when you are calculating also number of parameters. So if your input image it's RGB, so in this case, number of parameters will be 3 times 3 times 3 times 32 plus 32, right? So, but as you can see in the code, when we select the filter size, we select it 2D, just 3 times 3. We don't select it 3D, in fact. It's only 2D, but it will be 3D if your input image is RGB. If your input image has 3 channels, for example, and it's the same for the next layers, for example. So the same also for the next layers, because if you will select number of features is 32, we can just say that the feature map will have 32 layers or 32 channels. So you will consider this number also when you are calculating number of weights of next layers. So the filters, in fact, they have weighted input and generate an output like a neuron. The input size is a fixed square called a batch or receptive field. I mean, this receptive field, it will be the size of your filter. 3 times 3, 5 times 5. I guess you can select this one based on the size of your input image. If the convolutional layer is an input layer, then the input batch will be pixel value. If they deeper in the network architecture, then the convolutional layer will take the input from a feature map from the previous layer. So only in the input layer, we will have number of the depth will come from the input image, but for next layers, it will be the number of feature maps. So the feature map is the output of one filter applied to the previous layer. A given filter is drawn across the entire previous layer, moved 1 pixel at a time. We will move it one by one, from left to right and from up to down, or top to bottom. Each position results in an activation. This is very important. Each time when we apply this feature filter to the input, we will have one activation. So, for example, when we have an image like this one, and we apply here this filter one time, so this is one activation, and after that we will move it one pixel. We will do another activation, another pixel. We will do a third activation, and so on. So we will move like this one. So each time when we apply this filter to the input image, we just call it one activation. And therefore, when we are use pooling, we will reduce the size of the input image. So it will be just divided by 4, in fact. It will be like this one. So we will get rid of this area. So the size will be reduced by 75%, right? And in this case, we will reduce number of activations, because when in the next layer after pooling, when we apply the filter, we will apply the filter to that part, only that part. So in this case, we will reduce number of activations. So if you want to speed up the learning process, try to use more pooling layers, because those pooling layers, it will help you, in fact, to reduce number of activations and number of calculations. So the learning process will be faster. If the receptive field is moved 1 pixel from activation to activation, since the field will overlap with previous activation by field width -1. It's important to have this kind of overlap between activations. So this is very important. So when you are selecting stride, you can say that, okay, my filter size is 3 times 3, and I will select the stride equals 3, which means each time my filter will move by 3 bits. So in this case, we will not have this kind of overlap between receptive fields or between activations, and it's not recommended, in fact. So you need to have some kind of overlapping between each activations. I mean, this is very important when you extract features. Zero padding is used to invent mock inputs with zero values for the receptive field not to read off the edge of the input feature map. I mean, last time we talked about zero padding. Zero padding is very important because if you will not use zero padding, in fact, we will scan informations or pixels at the edges and at the corners maybe very few times, and this is not very good, because maybe those informations are very important. If those informations are important, you need to add zero padding, so we can go through those important areas also more frequent. Last time we talked about what is the meaning. In fact, what is the meaning of those? No, I mean here. I mean, if you didn't use zero padding, the output feature map will shrink. In fact, it will shrink. If you want to keep the same size, if you want to keep it with the same size, we need also to use those zero padding. So zero padding, in fact, when applying the convolutional layers, we lose some pixels around perimeter of the input image. It can add up of successive convolutional layers. One solution is to add pixels of zero values around the boundary of our image. When we add those zero values, we can keep the size as it is. The stride, by default, the filter slides 1 pixel at a time. Sometimes for computational efficiency or because we wish to downsample, we move our window more than 1 pixel at a time, skipping the intermediate locations. I mean, this stride you can decide by yourself, and you can decide, you can check, I mean, you can see what will be the impact, because also, I mean, stride will impact number of activations, right? So if you want to speed up calculations, you need to select much bigger stride. By default, it will be 1 pixel, but if you selected it 2, for example, so in this case, we will have much less overlaps between activations, but the number of activations will be reduced.
Can I ask a question?
Yes, please.
After applying a filter, do we use any kind of activation function?
Yes, we use activation. Yes, you can use RA. You are selecting it, in fact, for each layer. So in those activations, imagine that those are the weights, right? We will apply this one to that part. So it will be 0 times 0 plus 0 times 1 plus 0 times 2 plus 0 times. So it will be 0, right? Plus bias. So this one, imagine that this value, it's a plus bias. So this value will apply it to the activation function. Maybe you are using RALU, for example. So so as I told you, it's a convolutional layer. It's one layer like this one. It's like this one. Number of neurons equal to the number of feature maps which you want to extract, or number of filters. And each neuron, in fact, it's connected with number of weights. Number of weights, in fact, it's the size of this kernel. So if this one 2 times 2, it means this one it's omega 1, omega 2, for example, omega 3, omega 4. So each one will be connected with a set of weight values. It will be like this one. Plus bias. We can just say we have bias. So this is the first one. So in fact, this one, I mean, the value calculated from this one, it will also go here 1 time, 2, 3, 4. I mean, each time when we move the filter, when we scan the input image, each time we will have 1 activation, and the result here will go to one of those pixels, resulting pixels of a resulting feature map. So how many neurons here? Number of neurons will be number of filters, right? It will be the number of filters or the number of feature maps which you want to extract. Yeah, so it will be like this one. So each time we apply, we make calculations. We have this average value or weighted sum, for example. It's weighted sum because it's omega multiplied by those pixel values. So it's weighted sum. And after that, we will add the bias and apply this value to the activation function. You need to select the activation function here. Maybe it's ReLU, for example, ReLU, right? Rectified linear unit or any other activation function. So I mean the activation function we need to select it by ourselves. But the idea here, if each time we apply this filter to this receptive field, we have one activation. Each time we have one activation. So we will move it by 1 pixel. So next time it will be here. We will do another activation. We will move it by another pixel value. We will do a third activation and so on. So each time, in fact, when we apply it, we have one calculations. If you want to reduce complexity, for example, if you want to speed up learning process, so instead of selecting stride equal 1, which is the default value, you can select stride equal 2. So in this case, if we selected stride equal 2, we will not, in this case, we will not have overlap because we will do the first activation here and we will move by 2 pixels. So the second activation will be here and so on, for example. So in this case, you reduce the overlap, but on the other side, you will reduce number of calculations or number of activations. So, so because you are skipping those intermediate locations, maybe it will have bad effects. So you need to test this. Yes. So I mean the pooling layers down sample. I mean we have some input, right? And this input image we apply some features. We do this weighted sum plus spikes. We do activation. So from this input image we will get this feature map. Imagine that this one is feature map. So before this feature map here we have activation. In fact, we have each pixel will represent one activation. Each pixel value will come from one activation, right? So and those number of activations, it will be based on, I mean, stride and other things. So after getting this feature map, we need to do this max pooling, for example, or average pooling. This max pooling, it will do some down sampling, right? So the size here, it's 3 times 3. When we do 2 times do max pooling, we will get this size, for example, this output image. This one, it's max pooling. So we will select, if it is 2 times 2, we will select the part and we will get the maximum value. Maximum value will be 4. We will move it by one pixel. So, and we will do here, we will get the maximum, which will be 5. We will go down by 1 pixel. So we will do it here. So the maximum will be 7. We will move 1 step. So the maximum will be 8. So it's max pooling. So the max pooling, it's down sampled the previous layer feature map. Pooling layers follow a sequence of 1 or more convolutional. So you can have 1 convolutional followed by max pooling or 2 convolution followed by max pooling. So this max pooling, it's important because it will down sample the feature map. And when we down sample the feature map, we will reduce number of calculations or number of activations. And it intended to consolidate the features learned and expressed in the previous layer. It's a way for generalization. In fact, we try to understand, we try to down sample and try to get some maybe higher level features. I mean, when you have an image, so instead of looking at it from very short distance, you try to look from marginal. You down sample it and you look from a distance. So almost you will not lose any information, but on the other side you will have more efficient model. So they compress or generalize feature representations and generally reduces overfitting of the training data by the model. I mean, it reduces overfitting because when we reduce number of, when we downsample each feature map, and when we flatten at the end, number of, I mean, the size of at the end, I mean, before feeding those values to the fully connected layer, I mean, the size will be affordable, in fact. So we try to simplify the model or to reduce model capacity by using this max pooling. So I mean, so this max pooling, it will consolidate the features learned. It will compress or generalize feature representations and generally reduces overfitting of the training data by the model. They have also receptive field, which is much smaller than the convolutional layer. It's, I mean, by default, it's 2 times 2 with a stride equal 1. receptive field is moved from for each activation is often equal to the size of the receptive field to avoid any overlap. Pooling layers are often very simple, taking the average or maximum of the input value in order to create its own feature map. So in fact, this pooling layer, it does not have any weights. It does not learn anything. It's just max pooling or average pooling. And maybe, I mean, we need to try different types. I have no idea, but it should be possible to try different combinations or different. So, of course, we cannot use minimum pooling because if it is minimum, we will select 0 all time. So, so this max pooling, it does not have any parameters. So when we are calculating a number of weights, number of trainable parameters in our model, we don't consider this max pooling because max pooling, it's just calculations and it does not learn anything. It does not have any parameters. So what about fully connected layers? These fully connected layers are the normal flat feed-forward neural network layers. I mean, we know those fully connected layers. So those fully connected layers, it's something normal, similar to feed-forward neural network, which we have been using in shallow learning. These layers may have nonlinear activation function or softmax in order to output probabilities of class predictions. I mean, usually here in the middle, you can use RALU, for example, and at the end here, if you are calculating probabilities, we can use softmax. And when we use softmax, you can just say, you can call it softmax layer. So here in the output layer, if you are using softmax activation function, you can call it softmax layer, for example. So in the input here, we have the input volume. It's 32 times 32 times 1 because it's one channel. So this way, it's a grayscale image. You can just say that this image, it's a grayscale image. We have some convolutional layers with stride equal 1. We have some max pooling, and after max pooling, we will have flatten. So when we flatten this one here, I mean, each value will be representing a pixel value from resulted feature maps. So here, for example, we have 14 times 14 times 3. So the number of outputs here will be 588, which is 14 times 14 times 3. Is it correct? Or I don't know if we are using max pooling after. What is 14 times 14 times 3? Yes, so it's 588 in fact. So, I mean, this flatten also, it does not have any parameters. It's just one layer, which try to put those output feature maps into the correct format for fully connected layer. We just flatten it. We just flatten. So those 588 values, pixel values, are in fact 14 times 14 times 3, right? So the output here, we have 3 feature maps. In the output here, we have 3 feature maps because this one, it's 3 layers. And the width and width and height is 14 times 14. These layers may have nonlinear activation function or softmax activation function. If you are using softmax, you can just call it softmax layer. Fully connected layers are used at the end of the network after feature extraction, and the consolidation has been performed by convolutional and the pooling layers. So we have feature extraction and the consolidation by pooling, max pooling, for example. So they are used to create the final nonlinear combinations of features and making predictions by the network. So maybe you heard about transfer learning, for example. So transfer learning, I mean, training those feature extraction layers, it takes time. This is the most time-consuming part, right? This is the most demanding part in terms of computational resources. So if you have a model which has been trained for some other problems, you can transfer it into your problem, but you need to change the softmax layer. So imagine that so someone has been using a model for MNIST dataset. So if we are building a model for MNIST dataset, so the size of the softmax layer here at the end, it will be 10 classes, because in MNIST dataset we have 10 classes. If someone else wants to use the same model for classifying the dogs and the cats, in this case we have 2 classes, so I need to change the softmax layer, in fact. So just keep the model as it is, and just try to change the softmax layer. Try to customize this one into your problems to fit your problem. So I can borrow a model which has been trained for classifying MNIST dataset into 10 classes, for example, and I want to use this model now for a different problem which has 2 classes, cats and dogs. So in this case, I need to change. I cannot use this one as it is because this one has been trained to extract features from the image and classify each image into 10 classes. But my current problem now, it's the same, but the difference is that I have only 2 classes. I don't have 10 classes. So in this case, I need to change the softmax layer into 2 classes, right? And just to train.
Sorry.
And just, yeah.
What if we want to make a regression based on some pictures? It's like the input of our model is a data set of pictures, images, and we want to make a regression based on that. In that case, which activation function we should use, or we could use it fully connected layers or not? Can you help me with that? It's like the activation function is for different decisions making, right?
Yes, it's only softmax. It will give you probability. So it's only softmax. So you can just use any other. You can just use RELU, for example, if you try to regress positive values.
Yeah, for regression,
right?
It's better to use RELU, right?
For example, if you are sure that you are regress positive values, because RELU, the output from RELU will be positive all time. So instead of using softmax, because the output from the softmax, it will be a number between 0 and 1. And it's normalized, in fact. So the summation of those softmax values, it will add to 1, in fact. So the summation of class 1, plus 2, plus 3, 4, 5, 6, 10, it will add to 1 because we normalize it, in fact. So we divide each value by the summation of all 10 values. So at the end, the summation will be 1 because it's a probability that this image belongs to this class. So if it belongs to one class by, for example, 80%, it should belongs to the other one by 20%. So this is softmax. But if you want to use this problem for regression, we just need to use different activation function. Yes. But the idea here, if you want to use a model for solving another problem, we call it transfer learning. So I will use a model which has been trained for some other problem, and I need to modify it or tweak it to fit my problem. So if my problem has 10 classes, if this model has been trained for 10 classes and I want to use it for my problem, which is 2 classes, for example. So in this case, we need to change the fully. So maybe the output layer, this softmax layer, and instead of using 10 classes, I can just modify it to classify each image into one of 2 classes. So I need to change it into binary classification problem. So in this case, I need to change this one. And I will look the weights of those those convolutional layers because I don't want to damage it, because those those convolutional layers has been trained for some other problems and it takes time, for example. So in this case, I don't want to. I want to keep those weights as they are, in fact, and I will just try to adjust or fine-tune the weights of the fully connected layers. For example, maybe all of them or one of them, 1 layer or 2 layers. For example, usually maybe they use 2 layers. For example, I mean the output layer and the one before it. For example, try to change those weight values to customize this problem to fit or to match my new data set. So deep learning in Keras is very, very good. In fact, it's very easy to use. In fact, so Keras provide very good implementation of convolutional layers. We call it Conv2D, and it's Conv2D, in fact, for all models, except maybe 1D, which can work with time series. 2D, we can use it for images, 2D images or 3D images. For example, it's not 3D images, but RGB images, for example. So it requires the expected shape of the input image. We just need to define the expected shape of the input image in terms of height, width, and number of a channel or depth. And the filter contains weights that must be learned during the training of the layer. The filter weights represent the structure of the features that the filter will detect, and the strength of the activation indicates the degree to which the feature was detected. So the layer requires that both the number of filters be specified and that the shape of the filter be specified. So we just need to specify the shape of the size, the shape of the filter. So what is the size of your filter? It's 3 times 3, 5 times 5, for example, and also number of filters. Each filter will help us to extract a different feature map. So we need to specify how many filters do you want to apply, for example. So the building blocks of Keras, in fact, we just need to use maybe sequential APIs from Keras.models. We have also model API. I told you this model. It can be used for defining temporary model, which can be used for plotting some intermediate values. I mean, if you can remember, I used this one when we trained autoencoder, because autoencoder, after training it, I want to divide it into encoder and decoder, right? So after training your encoder, you can define a model from the input to the code, or from the code to the output, for example. So if you want to use it for denoising or whatever, so I used this model API for defining some intermediate values or some submodel, for example. From Keras.layers, we need to use dense layer. Those dense layers, we use this one for defining our fully connected layers. Conv2D, in fact, it's for convolutional, and the max pooling or average pooling layer, and the flatten layer, in fact, we can have also flatten layer. So this is how we build the model. You just need to define a model using sequential API, for example, and you need to add different number of layers. You can add dense layer, you can add Conv2D layer, for example. If it is dense layer, for example, you need to define number of units, number of neurons, for example. What is the activation function, the dimension of the input, right? And so on. After defining or after building your model, you need to configure your model. And to configure it, you need to define what is the loss function, what is the optimizer, what is the metric, which will be used for assessing the performance of your model. And after that, you will train your model using your trained data set. You need to define number of epochs. You need to define also the batch size, for example. So there are many parameters if you want to go deeply into it, but there are some default values which can simply selected. And after training your model, you need to evaluate and predict. You need to evaluate the performance of your model. So we have this evaluate, and this evaluate, if you want to evaluate your model using the test set, for example, you can just do it. If you want to do some evaluations for the training set, you can do it. And after that, you will use this your model for making some predictions. We can just say this one, it's deployment or prediction, for example. So you'll apply some X test value, and you will predict some classes and so on. Yes. So last time we have been talking also about how can we understand the convolution, what is convolution, and I give you some examples about edge detection, for example. There are some filters for edge detection. So edge detection, it's used for image segmentation, and it creates boundaries of an object to detect the object location, for example. So you have some input image. We can define a filter for vertical edges or horizontal edges. We can detect vertical edges or horizontal edges using some filters. This is an example of vertical edge detection filter, and it's 6 times. We have some 6 times 6 input image. Positive or non-zero values, it will be white pixel, and the 0 pixels, 0 values will be black pixels. And we want to try to predict this edge, which is located here. So if you will apply this filter to this input, you will get this output feature map, for example. So it will be white at the edge and the black, otherwise. So in this case, we will be able to predict those vertical edges. So there is filter for predicting vertical edges. There are some filters for predicting. We will do it like this one. So do you see? It's convolution, in fact. So first we will apply the filter to that part. Is this receptive field, for example? And we will just, it's weighted sum, just to multiply all those weight values. I mean, the weights here, it's 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. So we will apply this one to the this receptive field, and we will calculate the output value, and we will put the output value here, for example. So it will be 0. We will move it by 1 step. We will do this calculation one more time. So in this case, we will get 30. I mean, 0, 0, in fact, it's black, 30, it's positive value, so it will be white, right? We will move it by 1 step. We will do this calculation one more time. So we will get 30, which is white. we will do it again one more time. So it will be 0, and we will go down by one step, and we will repeat this process until we are able to predict, in fact, or to detect the vertical edge. So at the end, this is the output feature map. You can just say that this is a feature map, and from this, and this is the input image, and when we apply this filter, we will be able to detect those vertical edges in this image. So this is one example of one filter. Imagine in deep learning, I mean, you don't do anything. In fact, you just need to decide how many filters we need to use. And all those filters will be initialized by random values. And the learning algorithm will try to adjust those weights in a way to get some feature maps, which can help the model to solve the problem in a nice way. So this is how filters works. So there are lots of edges. In fact, you can just open any image processing book. You can find lots of filters. You can just search for it online. Vertical edges, there is some filters for vertical edges, for horizontal edges, for example, and so on. So there are many filters. But how many? It's very limited, in fact. So when you try to search literature for number of filters which people use in daily life, it's a very limited number of edges. But in deep learning, in fact, it's much easier, in fact, because you just need to define the size of your filter. So it will be 3 times 3, like this one. Those values will be weight values. It will be omega 1, omega 2, omega 3, omega 4, omega 5, omega 6, omega 7, for example, omega 8, omega 9. So we will have those values. Plus bias, remember. So it will be like omega multiplied by pixel values plus B. And after that, we will do some activation, right? We will do some activation function to get the pixel values, the output pixel value. So those weights will be initialized by random values at the beginning, because I don't know, should we select those weight values by 1, 1, 1, 0? I don't know. Do you want really to extract vertical lines or horizontal lines? What kind of lines you want to extract? We don't know. We will leave it for the CNN model to decide what kind of lines you want to detect, for example, what kind of features you want to extract. So the model will do it by itself. So this is one example for just one filter. And you can just imagine if I will use 32 features or 64 features or 128 filters, you can just say, now I want to use 128 filters. So those 128 filters will be defined, will be initialized by random values, and those weights will be adjusted using backpropagation, right, in a way to extract something useful to minimize the loss function, right? So we will leave it for the optimizer. So if we can go back to this Keras here, sorry, it will take time. So we have this building blocks. We will build our model, and we will leave this task, in fact, for the optimizer. We select an optimizer, and this optimizer will adjust the weights in a way to minimize this loss function. We need to minimize this loss functions. So we will start by random values, and we will calculate the loss function. And after that, maybe the error backpropagation will try to adjust those weights in a way to minimize this loss function, which we. So after some iterations, after a number of epochs, maybe the model will be able to extract meaningful features which can help us to solve the problem. Yes. This padding, we'll talk about padding last time. Padding, we just add rows and the column of zeros, right? To just, keep the size of the feature maps. Because if we didn't use padding, feature maps size will shrink, and we will lose some information across the perimeter of the image. Maybe this information are very important. If you are building a machine vision for quadcopter or autonomous car, the information, in fact, at edges or at corners are very, very important. If your model will not take care of the information which are coming from edges, maybe we can make an accident, for example. So in this case, we can use padding. And padding, we have two choices. In fact, we have something called valid or same. So when it's valid, in fact, we don't apply padding. So the size of the feature maps will shrink. And then when it's the same, we will apply padding in a way to keep the same size of the input image. Stride also, I mean, we'll talk about padding. So we have padding, we have stride. So I mean, if you know the input size, if you know the padding, if you know the stride, if you know the filter size, you can calculate the size of your output image or output feature map, for example. Yes. This one, it's a stride convolution of size 2, for example. I have this filter. We have those numbers, those weights. Imagine that we got those weights, in fact, after. I mean, I wish today, in fact, if some of you can try to train a model and try to print out those weights, so we can know what kind of filters we are using. So we can just, for example, work with MNIST dataset and maybe select maybe 4 filters or 6 filters, small number of filters, and we need to train the model. And after that, we need to print those values. We need to know what kind of filters the model has been, I mean, deciding for us, for example. If you are using this one and the stride size is 2, number of calculations will be 9, in fact, right? We are not using padding here, so the size of the output image will be shrinked, and also number of calculations will be much less. So those number of calculations or number of activations, it's based on the stride, in fact. So this stride, maybe it will impact the performance, not maybe, of course, it's the performance, so the model will train faster, maybe, or maybe it will not be able to train, I don't know, because we will miss some information here. In fact, when stride equal to, number of overlaps will be less, number of activations will be less. So we need to check what will be the impact on the performance, accuracy, and so on. Yes, so we apply it for the first time. We calculate those weighted sum, so it will be 91. I mean, we didn't apply activation here, but you need to apply this one. You need to send this one to the activation function. If it is ReLU, for example, but of course, ReLU, maybe it will be the same value. It will be 91 because ReLU, it's like this one. It's linear function, right? So when we have this one 91, we will get output will be 91, right? But if it is negative value, it will be just converted into 0. But of course, we are working with images, so we will not be able to get those negative values. So we will move by 2. Now we moved by 2 steps because the stride equal 2. So the output will be 100. Again, we will move by 2 steps. So we will get 83, for example. So we have here 3 activations in the first row. Next time, we will go back by 2 steps. We will do one more activation. We will get 96. We will move again one more time. Third, 7, 8, 9 times.
I'm sorry, the default stride value is 1?
Yeah, it's 1. By default, it's 1, but you can select different stride value.
Okay.
Yeah, and if you will select a different value, it will impact the number of activations. So maybe, and the size also of the output, I mean, the size of the output image, in fact, because now we are moving by 2 steps, so the output will be 3 times 3. If you are moving by 1, imagine that you are using by 1, so this one be the first pixel value. It will be this one. We will move by 1 step, so we will get this pixel value. Again, 3, right? 4, 5, 6, 7, 8. So it will be 8. So it will be 8 times 8 if you use the stride equal 1. Now it's 3 times 3. So stride, in fact, it has impact on the size of the output feature map and also number of activations. Because in fact, each activation is a pixel value. Each activation will result in a pixel value. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. So it will be 7 times 7. In fact, it will be 7 times 7, right? Okay, we will do it here. 1, we will go back. 2, 3, 4, yes. Yeah, it will be 5. In fact, the output will be 5 times 5. We will do it here 1 time, 2, 3, 4, 5. So if you use the stride equal, if you use the stride equal 1, we don't use padding here. So the output image will be 5 times 5. I mean, the output image will be 5 times 5. If you use the stride equal 2, the size will be 3 times 3. But the input image, in fact, it's 7 times 7. This one, it's 7 times 7. Because we are not using padding. If you want to keep the same size, in this case, we need to use 0 padding, right? So if you don't use padding, I mean the output, the size of the output feature map will shrink. If you use the convolution stride equal to, it will impact the size. The size will be much less, right? Size will be much less. Number of activations will be much less. Number of calculations will be much less.
If we want to use the padding, the matrix size would be 9 multiplied by 9.
Yeah, yes, this one, it will be 7 times 7 if you use the 0 padding, right? So so we will add 0 here. We will add a column and row from each side. It will be like this one, right? So so 1, 2, 3. It will be like this one. So this is the first time, right? So it will be first time, second, third, fourth, fifth, 6, 7. So this is the last time. So it will be 7. If you are using stride equal 1, if we use the stride equal 1 with padding, right, which is same, padding equal same. So in this case, the output image will be 7 times 7, right? So it will be the same. The output image will be 7 times 7, the same as the size of the input image. If you are using stride equal 1, and if you are use padding equal same.
Okay, the padding that by adding zeros, with that one, how many the final matrix would be, the size of the final matrix?
So it will be 7 times 7.
7 times 7?
Yes.
Oh, instead of 3, instead of 5 by 5, right?
Yes, because 5 times 5, we use a stride equal 1, and we don't use padding, right?
We don't use.
We don't use padding. But if you will use padding, it will be the same size as the input. So just if you want to, because if we will apply it for the first time here. So if I'm using 0 padding here, so I will apply it for the first time here to calculate the value here. So this is the first value, second value, third, fourth, fifth, right? 6 and 7, right?
Yeah.
So this is the last time, last activation, for example, if we are using 0 padding. So we will scan the whole values. I mean all values, and we will keep all those values in edges, and so it will be the same size if you are using 0 padding.
Thank you.
And the stride equal 1, right? And the stride equal 1. If you will use 0 padding and the stride equal 2, so this one will be the first time, and after that I will move 2 steps, so it will be the second time, right? Third time. Sorry, it will be, this is the first time. We will move 2. It will be here. We will move 2. It will be here 2. Maybe 3. Yes. So it will be maybe 4 times 4. If we are using 0 padding and the stride equal 2, it will be 4 times 4. Yeah. So just, I mean, this stride, it has a huge impact on the number of calculations or number of activation, and also the size of the output image, right? So, okay. So convolution over volume, this is very important. If your image is RGB, if your input image, it's RGB image. When it's RGB, in fact, we have 3 layers or 3 channels. The depth equals 3. So the filter also will be 3 times 3 times 3. It will be one for each channel. So the filter will not. So if you are selecting, but in Keras, in fact, you select only 3 times 3. You don't need to you don't need to say that this one it's times 3 in fact, because it will understand it from the input volume, from the size of the input volume of your raw data. But just remember, if the input image it's a volume, and if it is RGB image, for example, so the filter would be 3 times 3 times 3, one for each channel, and the output will be, do you see the output? It will be one channel. I mean, the output feature will be just one channel. So it will be weighted sum. This one, we will have this weighted sum multiplied by, look, we will apply it here, for example. So we will have this one here multiplied by that part. And after that, the other one will be multiplied by this one. The other one will be multiplied by this one. We calculated the weighted sum plus bias. So we can just imagine it as a perceptron. And this perceptron, how many weights will be connected to this one? It will be 3 times 3 times 3. It will be 27 weights. So it will be like this one, omega 1, omega 2, until omega 27 plus bias, for example. So it will be like this one. So it will be one perceptron, which is connected not with 9 weights, but it will be connected with 27 weights. The 27 weights, they are coming from this filter. Each filter, it's a 3 times 3 times 3. So it will be 27. And we will apply this one to the 3 channels each time, each activation. Calculate the output pixel value here, and repeat this process each time. So the output volume, in fact, it will be one channel, right? It will be like, but of course, you select how many filters. So the filter will be 3D. In fact, the filter will be 3D, but how many filters? If you have only one filter, you will get this one. If you have 64 filters, you will get 64 feature maps from this size. Mm-hmm. Is it clear? So instead of 2D image, we have 3D input image. So the shape is 6 times 6 times 3, for example. It's a height, width times a channel or depth. How we will apply convolution on this image? We will use 3 times 3 times 3 filter instead of 3 times 3 filter. So the number of a channel and the depth of filter will be the same. After convolution, the output shape is 4 times 4 matrix. So the first element of the output is the sum of the element-wise product of the 27 values from the input. It's 9 values from each channel and 27 values from the filter. So we will have, each filter has 9 values. Those 9 weight values will be multiplied by 9 weight values in each channel, and we will calculate the weighted sum for the 27 values at the end, adding the bias and applying this value to the activation function. So each activation will result in a pixel value in the output volume here, in the output feature map. So after doing this one convolve over the entire image, we will get this feature map. So just please, when you are in Keras, don't worry about this. Don't worry at all about this one. So if the input RGB, it will automatically add the third dimension, in fact. So the number of filters will be the same as the depth of each channel. I mean, the size of the depth of the input image. Yes. Of course, I mean, here we use the one filter, one single filter, in fact, but usually we use multiple filters, and each filter will generate a different feature map. So if you are selecting 2 feature maps, you will get those, which means you are using 2 filters, right? So each filter will generate a value. Each filter will generate a value, so you can just select number of filters. Not the depth of each filter. I mean, the depth of each filter will come from the depth of the input image, but the number of filters, it's something which you need to specify. It's a hyperparameter. So 2 filters will generate 4 times 4 times 2 outputs, in fact. 2 feature maps, right? And each feature map has a size of 4 times 4. So it's just, I explained this, in fact. So I told you that it looks like a perceptron. And this perceptron, it will be omega multiplied by an input image multiplied by bias. So, and after that, apply the activation function. So, I mean, this, we understand this one, in fact, now. Pooling Pooling layers are generally used to reduce the size of the input and hence speed up computation. Because why speed up computation? Because in fact we will reduce receptive, not receptive field, we will reduce number of activation. When we reduce the size of the input consolidate those feature maps, consolidate those features, in fact, we will try to consolidate and try to reduce the size of the feature map. And when we reduce the size of the input of the feature map, we will speed up computations because we will reduce number of activations. We will reduce number of activation. And also, if you apply filter or stride, I mean, we described it already. So if you will increase the stride, and instead of using 1, you can make it 2, for example. In this case, you will reduce number of overlaps, and you will reduce number of activations. So you will speed up calculations. All those are hyperparameters you need to select. Yes. Should we take a 5 minutes break, for example, and after that we can start with this AlexNet example? Is that fine? Can we take 10 minutes break? We can start again at 10:20.
Sure.
Yeah,
Yeah,
sounds
okay.
good.
Thank you.
Thank you.
Okay.